Thanks so much for having me. Thanks so much for the awesome introduction. So there you go. So I want to divide these studies into like three things. I'll talk about dyadic and triadic interaction, but also like this idea of internal interaction, which I'm having right now. And so there could be many kinds of interactions, resting state, mind wandering itself, problem solving. But recently we did this project where we made people watch their own interaction with others to see whether we can capture like some idea of like how reflection should be done to improve your own performance versus how people may get stuck in this ruminative tendency. So we wanted to get a handle on that. Credit goes to my grad student in the lab, Caleb, Janice. And so the idea was you take a bunch of people. So this is in collaboration with Center for Design Research at Stanford, where just do crazy stuff as well. And so the idea was you bring in 3 people, let them solve different brainstorming problems, like design challenges we called it, where they would brainstorm, they would prototype, they would kind of create something, some prototype for the problem, and then they would present it, the whole design thinking process. And then later on, we would record everything, and later on, these same people would go in the scanner, but one by one, and then they would see their own performance and how silly jokes they were making inside and get mad at themselves. But also, like, we wanted to see, and then we asked them to, once they see their own videos, kind of sort of reflect on them, and then think of ways in which they could have improved themselves, or they could have done a better job, or maybe somebody else could have done a better job, stuff like that. And they get out of the scanner, and then they give us a recall of what they were thinking, so on and so forth. So this was the idea. So each team, again, like did this design session first, then they go and do this, take part in the scanning. And I think I have to mention Sahar. She was one of the RAs in the lab. She did a great job in like collecting all the design data. It was a big challenge to even collect these data sets and parse them and put them in the scanner and all the annotation stuff that goes with it. But then the main idea is you see your own videos, and we kind of chopped it to find like interesting pieces in the conversation, which we thought were interesting at least. And they would see themselves and then reflect, and then see themselves again, reflect, and then see a control video, which they're not part of, and then reflect. So, and then just for fun, to make sure they're kind of not sleeping inside the scanner, we would ask them, okay, what kind of interaction do you think is going on? Is it humorous? Are they fighting? Blah, blah, blah. And then they reflect. So these are some of the initial results we have. And this is an interesting problem for the ISC, because 3 people see the same stimulus, but not everyone. So we couldn't do a standard ISC. So this is an ISC hack, I should say, where we kind of get for each brain region, get this subject by subject matrix, but then take the subject-wise max. And it turns out more often than not was from the same team. So hopefully reviewers won't mind. And we found that the control video luckily was the same across all people, but the self-viewing would change. But we found that these brain regions apparently had higher ISC. I was hoping to get like DMN and stuff like that. We didn't get any default mode network, but these are the regions we found. So if you guys have any cool ideas about why they show up, I'm happy to talk later as well. And then we did this crazy thing called TDA, topologic data analysis. And the idea here is you take the data, and kind of look in the time dimension rather than space dimension. So typically we look for, which brain activity area or which connectivity goes up and down with the stimulus. Here we transpose the matrix. So for the analysis, we want to look at the shape of the data. So the idea being that, let's say you have 1,000 time points in the scan, or 1,000, however many samples that you're acquiring, and you have columns as your brain regions. And you want to kind of see how each individual time point is similar to every other time point in the brain, every other time point in the entire session. And I'll talk more about it in the tutorial, how we do this, but roughly each node in the graph is, let's say, representing that time point in the scan time. And the bigger nodes are points where spatial activity whole brain activity was so similar that it get coalesced into bigger nodes. So there's no averaging happening here, it's just a representation. But when we create these kind of graphs, the cool thing is you can then annotate the graphs based on any meta information you have. So here, simple meta information is like what it's doing. So videos themselves, or the reflections, or even the fixation points. Like you can color it however you want. And one way we color here is this. But you can do any kind of coloring, from like which resting state networks pop up in those TRs, or were they viewing themselves or not, or task or topological property, because it's a network at the end of the day. You can annotate it by all kinds of networks. And the idea is you're capturing this manifold of how your brain traverses in time, and has some repetitions, because sometimes the same state reappears, and that lets us pick up on these state transitions with a single TR level. And I wanted it to be a quiz, but I couldn't, I guess. So showing you two people, and then by the way, on the same project, we also acquired like a self-reported RRQ scale, rumination reflection scale, or reflection rumination scale, just to see if trait rumination can be picked up. And the idea was people who have higher rumination may have more sticky dynamics, so to speak, meaning their states don't change as rapidly. And this is just showing you two subjects out of 30 or so subjects, where the one on the left was high on reflection but low on rumination, and the one on the right is the other way around. And turns out we found this kind of more often than not, that people who are on the higher end of rumination ended up having a bigger core, which kind of represent that they had these brain states that are highly repeatable, happening again and again. And you can quantify it in many ways. One way is to just look at the degree of the graph. And we found that the degree was kind of related with rumination. But interestingly, even the control was like barely significant, but not significant actually. But the self-viewing, whenever they were watching themselves, at that time, their stickiness was more related with rumination than when they were watching control videos. So that's something Caleb is finalizing up and writing up for the paper.
In terms of, so the task was to reflect on your interactions. What is the likelihood, and I'm just, thinking about the consequences of the Zoom era, of people who are higher on rumination are just sort of also observing themselves, right? So they're kind of like, oh God, do I look like that? Do I sound like that? As opposed to their interactions with others.
Yeah, good point. Thankfully, because we are so lazy, this data was collected before COVID.
Oh.
We're finally analyzing it. Laziness helps. But you're right. Yes, people, if you do the study now, it's actually fun to do it now, like pre-post-COVID, and see how people differ.
It could have also happened before too. It's just that before we weren't even aware that like watching yourself is a strange experience.
It is, right? And at least when we were prototyping it, and when I went in the scanner, all I was thinking of how silly jokes I make, and then why was I wearing that shirt for some reason. But then that's why we kind of prompt them afterwards. Okay, reflect and remind them. Your job is to kind of come up with ideas, and every time you come up with an idea, just tap a button, and then you get out of the scanner and you recall. So there's some hope that they're not just thinking about what they're wearing, but actually focusing on the.
Or that there's kind of variance in that measure. And, perhaps the high ruminators are kind of stickier on that point. And that's
a good point. Yeah, so we haven't analyzed the speech data yet at all. So maybe with your awesome deep learning stuff, we can look at the thought space trajectory or something. That would be cool. Yeah, good point. Okay, so dyadic interaction. When I was a postdoc in Alan Reese's lab, I briefly played a role in this. And then now they are doing more naturalistic stuff. But at that time, we were just looking at how simple motor coordination can we pick up neural correlates of that. And he's really big on FNIRS, which is this optical neuroimaging technique. If you guys don't know, it's like you have source and detector, you send a light, detector receives it, and you get some idea about how it's like poor people fMRI. Basically it measures the same thing as fMRI, but very low dynamics or temporal resolution. And we, Ning Liu and Joe Baker led this work, and they had like 111 dyads. And they wanted to actually see sex differences in this very simple task. And the task was you get, set, go. So you see this gray thing, you get ready. And then when the green thing comes, both have to press the button at the same time. The sooner you press, time, you're cooperating, you get more points. There's a control condition like competition where you have to beat the other guy versus cooperating. So if you both press within the window, you win, both win, otherwise nobody wins. Very simple task. And they wanted to see how male, female, or female dyads would differ on this. And in this study, I found out that thankfully this attractiveness scale, apparently that matters a lot. So whoever is your dyad when you're doing hyperscanning, keep that in note as well. And the other thing we found out kind of post-talk was how many people play video games play a massive role when you have these kind of motor coordination tasks. And the other thing with NEARS is you cannot really get the full brain coverage. I mean, with the newer versions you can, but at least with the older version we had at that time, you can kind of do a piecemeal job. So you find the regions you're interested in, here frontoparietal, and you just focus on them. And interestingly, we found, this is kind of maybe because of the video gaming effect, sorry for the tiny font size, but this is like the cooperation performance on the task. And apparently male win, male female wins, but somehow female has like the lowest cooperation. I don't know why. Again, it could be simply the video gaming effect. We found males significantly played more video games in their life, which makes sense, I guess. And maybe that was playing a role. But interestingly, we found that the brain regions that were syncing up was different in female versus male dyads. Apparently, the synchrony was found in the inferior prefrontal regions for male, but right temporal regions for female. And that the amount or degree of synchrony was again related with the behavioral performance. So this was a very early hyperscanning stuff that we're doing, looking at using a very simple game. And now Alan and his team, they have a cool group called SING, Stanford Interactive Neurosciences group and stuff. So they're doing much more fancy hyperscanning paradigms like tipping point, like how can you convince somebody else to change their opinion and stuff like that. So it's using hyperscanning. Okay, so towards the end, triadic interaction. This was really awesome, cool, fun project. I'm relatively more proud of. And we had two different games in it. One was just playing game of Pictionary. The other one was story completion task. And I've only talked about Pictionary data today. So we had synced up 3 GE scanners on the campus, and 2 of them were in part of the medical school. One was in psychology, and it was the biggest challenge was how to sync them up because medical school had way too strict firewalls system. So we end up, I don't regard this stuff, hacking some stuff and making sure it works at the end of the day. But mostly kind of going to the Wi-Fi, and then Node.js and Socket.io, and we use Canvas API, so people could actually go inside the scanner and sketch. So Pictionary is a game where you don't know, you sketch, and somebody else has to guess the word that you're drawing. So we have this whole talking about issues. We're not maintaining it, but that thing is there if you ever want to play with it. Theoretically, you can sync up to 10,000 nodes without a problem. Apparently, that's what Google at least claims. So you can test it out. And don't blame me too much for the code if it doesn't work, because at that time we had our first kid and the only kid after that. And I was like totally sleep deprived. I wrote everything without sleeping, I think. Somehow it worked. I have still no idea how. And this was the paradigm. So when you go inside the scanner, it's these 3 people. Every trial starts with drawing the word yourself. So let's say in this case, the word, I don't know if you can guess the word. Can anybody guess the word they're trying to sketch here? Well, you guys are awesome. Cool. And then there was a control word. So you do this independent drawing, and then you evaluate other people's stuff. So this guy sees the other 2 people and so on and so forth. And you just kind of highlight things that you liked about the other people's design. But remember, we only gave them like 30 seconds. We're pretty fast in that respect. And then the collaboration piece starts where the screen is now shared. So previously the screen was, you don't see other people's screen, but in the collaboration phase, you stick with the same word, but now everybody can see the screen. So like when you take turn to draw, so this guy's drawing and these 2 are watching to draw. So they're kind of playing the game of Pictionary as a team with the person in the control room. So they're not playing with each other. So I misspoke. and then the other person draw and the other person draw. So you can see like people would like take the drawing and add on it and so on and so forth. And in this drawing, they were very collaborative in some ways, but in some cases, we also found people who kind of ignored the person's idea completely and drew their own thing. But so we could, we haven't done like detailed analysis, but you could see where people would either keep their own idea or they got somehow more excited about other person's idea during evaluation phase and use that. So you could do all kind of fancy analysis on top of it. And so first thing we did a basic ISC analysis, just real versus fake triads, just to find out which regions sync up. And a lot of regions sync up. And especially the RTPJ was very high effect size and also angular gyrus. And these two regions were kind of correlated with team performance. So team performance was measured by when the picture was done, final sketch, and then somebody outside rated it on how easy to guess it, how creative it design it, blah, blah. And this work was led by my postdoc, Huashi, got out in 2020. And then we did some crazy stuff, and it kind of stayed in prep for the last 3 years. Hopefully one day we'll finish this paper. But the idea is to now take 3 brains, so rather than taking 1 brain, take all 3 brains, append the data together, and now feed it to this TDA thing. And you get this massive graph, and then again, you can color it however you want based on which stage of the experiment they were. You can also color it by the players. So very simply, I just colored it based on which player, the row is coming from which player. And if you try to do that, you get different kinds of patterns. This is the entire experiment. So we didn't like chop off only collaboration phase, right? This is the entire thing going in. There are definitely better ways of doing this than just throwing everything on it. But the idea here we're trying to explore was, can we find the degree of overlap in these brain activities across people? And can that relate to creative performance or team performance? As I said, you can also color it by other things like where is collaboration happening. Apparently, it happened more in the center of the collaborative drawing versus independent drawing and so on and so forth. So here are all the 12 triads. And colored by the player. And just to help out, we find this 3 kind of, this is very qualitative, but we find like this very interesting triadic interaction, like some were more linear, some are more like when the other person is completely following the other person. We don't have a big sample size, very small sample size, but and some were where it was more like a 3-way interaction. And you can very easily quantify, or one way to easily quantify this is just looking at the modularity of the graph. So this is showing you TRs from all 3 players, kind of, it's a TR recurrence plot of like how similar each time point is to every other time point. And then you can kind of see some people were highly modular, meaning there was less overlap, and some were like all over the place. And the groups which are all over the place had like the highest group average team creativity, group average creativity, because and we had like 2 different creativity scores. One was just the drawing creativity, but we also had the individual creativity measured separately using a Torrance test of creativity thinking. So that kind of linked to that. Yeah. And towards the end, future work, we are kind of thinking more interaction with humans is cool, but what if interaction with non-humans like cars and or other AI systems? And this is like a race car thing I was trying, fun with so the idea, and this is again Alan's project, but the idea is to kind of hook the Formula One race car drivers with NIRS and kind of see how they do this awesome stuff. But the other thing, and mostly again, Alan is doing it, but I would love to be part of it, is he's working on this hyperscanning project with non-humans and like animals, like dogs, and how do dogs and animal brains synchronize. One of his pet projects. Pet is a pun. The other thing we're thinking about, like, how can we do interaction with brain stimulation? Like, because everything changes you, so maybe interaction can also change your brain in the way you want. And then last thing I mentioned briefly, I think it's like neurodiversity. And so the idea is, can we use these interactive minds or hyperscanning stuff to make teams like Jeremy was talking about, one person could have a knowledge gap here, the other person a knowledge gap here, and you kind of combine them the same way you could have somebody who has somebody like me who's good at generating ideas but not finishing things. There could be somebody else who likes to stick to one thing and finish it. And I'm still looking for that person, and then you kind of put them together. Do things. So just want to thank everyone, my team, Alan and his team, and funding and you guys and hiring. So in the tutorial, thanks so much. Any questions?
It's not really understanding PDA very well, if I could go over that next. So when you're doing it in the triadic interaction, is it basically that you have your columns or like circles,
Yeah.
all three people?
Yeah. So it's that matrix. So it's, maybe I had it. Yeah, that one. So space and time.
And then how, like, given the graph. So each node is a time point, or is the whole brain space
Yeah.
time point for a set of columns, or?
Yeah. So nodes represent the rows, right? So rows are time points.
Okay.
So the size of the node can vary as well. So if like brain activity across people or even within an individual, if it's highly similar, then they get to be represented as a bigger node. Size of the node goes up. This is one way to compress the data, but also help reduce the effect of noise in fMRI. I'll go into detail. Try to do that.
Edge.
The edge is so it's like this, and the idea is like the degree of similarity. If it's highly similar, they get coalesced as a node, and if they are somewhat similar, you get an edge. So you have parameters for these things.
Signal is out of 10 parts.
How is this group measure more very much orderly compared to individual graphs because you have like all over the place?
In the team, we didn't actually find much squiggles, didn't we? Sorry, I didn't get the question. Sorry.
It comes like the visualization still very much looks different. Like before, like individual ones.
Oh yeah. I see what you mean. Yeah.
But then here it kind of looks like a
Okay, yeah, it's a very good point. Yeah, so the issue is like, it depends how much data you have. So because here I had, it's like, I think at least 30 minutes per person times 3, so like 90 minutes of data. So the more densely you sample, the more dense the graph appears. So earlier it was like single subject data, and it's not very densely sampled, right? So you get, the less data you have, the less connected the graph is. So you get more squiggles and all that stuff. And also with a different kind of task. So we found that the resting state, the shape of the manifold is very different than when you do different tasks. So that also play a role. But it's like sampling, how much data points you have, and also the tasks you're doing. That changes the shape of the graph.
resting state scans. Does it has more? Does it have
I'm going to show you guys. That's what I have for the afternoon. Yeah, midnight scans of data.
Have you ever looked at like how TDA compares to like kind of manifold learning stuff like UMAP or?
Yeah, we did, and I'll show you some examples of that.
Okay, cool.
Yeah, I should have made this TDA talk, but then I thought that I will not talk about this.
I'm curious about like do you consider this as having like far benefits than other like time series analysis? Like
Great question for the afternoon. Yeah, I was sorry, it's all hyperscanning.
Plots, were those just from the cooperation phase of the task, or was that from all 3 stages?
I just took everything, but yeah, again, this is, if any of you wants to play with data or want to come to Stanford, let me know. It's just waiting forever. We collected this data in 2015. We can do all kinds of fancy things.
So you have these measures of creativity, but we have a measure of sort of performance or
Yeah.
success across.
So that was the final picture that they drew. So we actually have both. So each individual picture that they drew, we rate that, like how easy it is to guess the word. And second dimension is how unique it is compared to everybody else, novelty and usefulness. We multiply them to get the performance score. So we get both at the individual level because of independent phase. We get the team level as well.
And is modularity also predicting higher scores than that?
Double check which one. No, I don't think that was correlating with that one. That was only correlating with the average group creativity. At least wasn't significant. In fact, this project was actually born out of this science paper by Anita Hooley, where she had this idea, way cooler idea, but like you take a group of people and then look at their individual intelligence and figure out whether you can predict group intelligence based on the individual. And they found that if you have two very smart people in the group, then the group sucks. And so we were kind of banking on that idea. Like, okay, if you have two creative people who are very creative individually, then the whole team performance would also suck. So that's how it started. But we didn't realize you need like hundreds of people, we only like 12 tries. Statistically, it's very clear.
Luckily, no creative or interesting people.